Another quantity that's important to consider when thinking about momentum is impulse. And in order to explain impulse, we're going to go back to a collision scenario. This impulse applies any case, any situation where there is a change in momentum, but probably easiest to first of all think about a collision. So when dealing with a collision, the final and initial momentums basically result in a if we look at the difference between them, we have a change in momentum. So dealing with a single object, so we're not dealing with conservation of momentum now, we're just looking at a single object and the change in momentum that it undergoes. So the final initial momentum of a single object results in a change in momentum. And that change in momentum is otherwise known as impulse. So when you hear the word impulse, just think of a change in momentum that's occurring. So if we look at change in momentum, we'd represent that as delta P, and that would be equal to the final momentum, as is the case with any change. It's the final momentum minus the initial momentum. And in that scenario with a collision, we can consider that the mass is constant, so we could then write that another step and write the final momentum is as m times v and the initial momentum as m times u. So there's our change in momentum expressed in terms of the masses and the velocities, and you'll notice that we could then express that as mass outside of velocity, final velocity minus initial velocity. You may recall from an earlier video said had a brief mention of the fact that Newton's second law applies to momentum as well, and we're going to bring that up again now. So if we compare this scenario to Newton's second law being that if an unbalanced force acts on a mass, it causes it to accelerate. The more common way of understanding Newton's second law is through the equation F equals ma. Now if we look at this quantity of acceleration, that's really a change in velocity over time, so we could write that as m delta v on delta t, but again we can expand the change in velocity and write that as m multiplied by v minus u over t, and hopefully, delta t. Hopefully you can see that if we add the mass into the numerator, or not add, multiply the mass into the numerator, we end up with mv minus u in brackets. If we multiply the mass into the numerator, we get m outside of v minus u over delta t. Now we've already seen that m outside of v minus u is the change momentum, or the impulse. So we have an equation now for force, or for Newton's second law, in terms of momentum. So we can say that the force is the rate of change of momentum with respect to time. So that equation is an important one. It's in the data booklet, hence the highlighting. So Newton's second law in terms of momentum is F is equal to delta P over delta T. Taking that a slightly different way, if we're more interested in impulse, we can instead write that delta P is equal to force multiplied by the change in time that occurs. Again, it's another important equation, this time expressed in terms of impulse rather than being expressed in terms of Newton's second law. The units of impulse are the same as the units for momentum, given that it's just a change in momentum, so we could say that they are kilogram meters per second. But we also have an alternative here as well that we can find from this equation. So force is measured in newtons, so we can write the units of newtons, and time is measured in seconds. So an alternative here is Newton seconds. So both of those units are equivalent, so we can interchange between them. So 1 kilogram meters per second would be the same as 1 Newton second. So some important points to make here. the impulse that occurs depends on both the size of the force and the time over which that force is applied, or the duration. And if you think about what happens with a force, or with a change momentum, I should say. So again, if we go back to a collision scenario, we can think about a car coming to a stop from a speed of 60 kilometers per hour. Now, there are a number of ways that could occur. The first would be coming to a stop at a set of traffic lights, or maybe not the first, but one would be stopping at a set of lights. In that case, delta t is relatively long, so the force is relatively small. I'm using the word relatively here just to draw comparisons between the two scenarios that we're going to look at here. If the car comes to a stop from a speed of 60 kilometers per hour in a collision, so whether it's colliding with another car or with a pole or a tree or something or other, the duration of that collision is very short, and so the force, so F is relatively large. So in both cases, coming to a stop from a speed of 60 kilometers per hour, it's the same scenario. The difference is the duration over which the force is applied, delta t, and the size of the force itself, F. If you are thinking about a collision, there are another few things that we can identify here. Seat belts, airbags, and crumple zones are all designed to slow the passenger for just a little bit longer, or driver and passenger. And by saying slowing them over a slightly longer duration, what we really are saying is that in the case of a collision, we might be talking fractions of a second. If we can double that value of delta t, so even if it's say 50 milliseconds and we double that to 100 milliseconds, that's going to halve the force that's being exerted on the passenger and the driver. So just by increasing that duration, just even slightly, can have a dramatic impact on the forces that are experienced by the people in the car. So, like I say, conservation of momentum, impulse, all of these sorts of ideas aren't just interesting phenomena. They're very useful in the design of various safety features in cars, for example, and also in sort of situations, as we saw in the previous video, to do with propelling rockets, aircraft, all of those sorts of things.